This is when to use what, and we'll use this to wrap up the whole course. This is based on LaFour chapter 15. So at the beginning of the course, I said that most interesting programs operate on many data items. If we only have one thing to work with, we can probably get out a calculator and just pound it out quicker than we can write the code for it. But in general, that's not what happens with a program. We act on many data items. A collection of data is a general way to put it. In general, given a collection, we need to be able to add or insert into the collection, find something that's in the collection, or delete or remove something from the collection. And we can measure the goodness or speed, whatever you want to call it, using big O notation. We looked at a number of collections, and you recall we started with something very simple. We started with an unsorted array, and we looked at whether that was a good solution or not and compared it to a sorted array, and we went from there. And the way the whole course has been, how given a general collection of data items, what kind of performance do we get adding, finding, and deleting, particularly finding from it, and of course with some deviations. So this is LaFour's chart, his flow chart, and it's in chapter 15 if you want to see it there. And this is how LaFour goes about the task of deciding what to use. It's a flow chart. It starts up in the upper left-hand corner. He says, do you have a small amount of data? And if the answer is yes, we ask, is the amount of data predictable? And if that's yes, we can ask whether the search speed is more important than the insertion speed. And if it's not, we use an unordered array. That is to say we want to insert very quickly, and we aren't so worried about finding. If we want to find stuff in it, we answer yes to that. We do an ordered array. Coming back up a step, if the amount of data is not predictable, if the answer to that is no, then we use a linked list instead of an array. Coming back towards the beginning, if we have a small amount of data, no, we've got lots of data, then we say, is searching and insertion very fast? The answer is yes, then we need a hash table. The answer is no. We ask, is the key distribution guaranteed to be random? If it is going to fall out nicely, we use a binary search tree. If not, we use some kind of a balance tree, either a red-black or an AVL. And I can go one step beyond that, and I can say, well, if we're really more concerned about search than we are insertion, then we might say we use an AVL. AVLs stay a little more balanced than red-black trees, and if they stay a little more balanced, that would suggest that the extra cost in keeping them more balanced is offset by doing a large number of searches. Finally, LaFour doesn't cover it, but we had the splay trees. The splay trees have a similar argument to the balance trees, except we think we're going to go after certain elements a lot, right? So splay trees solve a slightly different problem. They solve getting at the thing that we used most recently quickly rather than something in general. So they're a little bit different. So this is LaFour's flow chart, and overall it's not a bad starting point. But for the most part, we're not going to worry too much about these things because hardware is faster, and we can just throw things into arrays, stuff like that, or we can use libraries. We'll talk about some of the trade-offs here. Why not just always use hash tables? After all, they're real fast, and they can deal with large amounts of data items. And hash tables are being used in a lot of new places. Objects in JavaScript and Python now use hashes to find the object variables. So when you declare a class in both of these languages, are a little odd about how they do classes. But you have an object and it has multiple variables in it. How do you find one of those variables? Well, in JavaScript and Python, you look up the name of the variable in a little hash table. There's a little hash table associated with each object. So they're being used in a lot of new places. But there are a couple limitations in hash tables, and you should keep these in mind. Know them for a test even. Two limitations. Hash tables are based on arrays, and that means that we need to know the approximate size in advance. We need to have some reasonable idea. It doesn't have to be that specific if we're putting up the phone book for New York City, that's about 10 million people. We don't need to know it down to the person. But saying something like, well, last year, 10 million people, we had 12 million phones, and rounding up a bit, we can get somewhere. And so that's not such a bad limitation, because in most cases we have some kind of guess. And it used to be memory was tight enough. I work for companies and we'd get to something and they wouldn't specify just how many of something there's supposed to be, and we'd spend all this time kicking it around. The reality was we were trying to guess whether something would happen 3 times or 5 times or maybe a dozen times. And these days you just declare it to be, say, 2 dozen or 64 times or 128 times, and you just figure I've got plenty of leeway. I won't worry about it. So the limitation about knowing the approximate size, we can be somewhat flexible there and get around that unless we really have no idea whatsoever. The more important one is that we can't need the items in order. If we have to organize it, for instance, the dictionary assignment, very often we want the words, we not only want to be able to find a word in a dictionary, but we want to list some of the words in alphabetical order. And at that point, the hash table is not going to work for us. We're just going to have to come up with something else. So that's the big rub on hash tables, is we can't get to things in order. How about graphs? We spent the last third of the course on graphs. So let's talk about that a little bit. You could argue that a graph holds a collection and therefore it's just another data type. But holding a collection is not the real reason that we use a graph. We use a graph to understand the relationship between entities. Okay? Given that, which graph representation should we use? We could do an adjacency matrix or adjacency list. Primarily, we want to look at sparseness. If it's sparse, we want to use the list. If it's not sparse, we'll use the matrix. And you can pin that down more by looking at the relative big O's. Quite often on a matrix, our big O has to do with the number of vertex squared versus the number of vertexes plus the number of edges. And that gives you a pretty good feel for sparseness. If the vertex squared is smaller than the number of vertexes plus the number of edges, we probably want to use the matrix. It's probably dense enough that we should just use the matrix. The other question, of course, whenever we run into using a matrix, using an array, is can we predict the size? If we don't have a good handle on how big it's going to be, similar problem to using the hash table. We can't really predict how big it's going to be, then we're probably better off using the lists approach. Okay. Weighted or unweighted, in most cases we optimize something that's represented with weights. That's usually why we're using a graph. We don't want to know if there is a path, we want to know the shortest or cheapest or quickest path. And if that's the case, then we have to use a weighted graph. But sometimes we just want to know if some relationship exists. We're not so worried about efficiency, we just want to know whether it exists. You may have heard of the Kevin Bacon game. This is a game where Kevin Bacon was a movie actor, and so you suggest another person involved in the movie industry, maybe a director or maybe another actor, and you try to find a path between Kevin Bacon and the other actor. You might say something like, well, Kevin Bacon was in this movie, and one of the other people in this movie was so-and-so once did a movie with this director, and the actor we're looking for did a movie with that director. So there's a relationship, an indirect relationship between Kevin Bacon and that person. There's also a concept called, I've seen it listed as both 6 degrees and 7 degrees of separation. This is an argument. It's a very interesting argument at the moment with all that's going on. And that is that any two people in the world, we can find a path between them using just 7 hops, 6 or 7 hops, depending on whether we think it's 6 or 7. So, for instance, if I'm trying to find someone in, where it would be very strange, Nepal, I can find someone that perhaps lives in India and knows someone in Nepal. I can go through, and there's the postulate that if we know the path to follow, that no one on Earth is separated by more than 6 other people to know each other. It's can be an almost scary thought at the moment. But if we want to just know if relationships like that exist, then we don't need to weight our graphs. We can use an unweighted graph. We can just count edges, things like that. But most of the time we want to optimize something represented by weights, and then we need a weighted graph. So within weighted graphs, we had two big theorems, right? Two big algorithms, I should say. Weighted minimal spanning trees versus Dijkstra. And how do we decide between them? Well, a minimal spanning tree optimizes a graph as a whole, okay, whereas Dijkstra optimizes a particular path within the graph. So it depends on what you're looking for. If you're looking for a particular graph, I want the quickest way to drive from here to San Francisco. That's a Dijkstra kind of a problem. If I just want to say, gee, I have this much money to work with and I want to connect as many towns as possible, that's more of a minimal spanning tree kind of a problem. Okay. Finally, advice on when to use what? KISS. Keep it simple, stupid. This is not very academic. We've done all the academic stuff, but I'm an old programmer, so I'm only so impressed by academics. I would say prefer simple solutions to complex solutions. If you have a small number of data items, use something simple like an array. There's no point in really constructing a lot of hash tables if you're going to have 3 or 4 items and you're not sure which, right? Now, I said a small number of items, so we can ask what is small? Well, it changes over time and environments. What used to be considered to be a lot is now kind of trivial and small, and instead of doing something involved, we could use something simple like a big array, because what constitutes a big array has changed. I was on a email project early in my career where it was very critical for us to, for business purposes, to put lots of users on a very small amount of hardware. Specifically, we were trying to put 100 end users using email onto hardware that had 16 megabytes of memory. And that was very challenging to do with some of the requirements we had. Worked very hard on it, did a lot of things to optimize performance, spent a lot of time worrying about keeping things small. For instance, using individual bits to store information for recipients, because you get lots of recipients. But now, you know, it'd be kind of silly to put that much time into saving a bit. Environments also change. Things are distributed now in a lot of cases, but it also means that what was old becomes new again. A lot of technique that went out of style on mainframes because the mainframes became large enough that it wasn't needed, all of a sudden were very useful when we had mini computers. And as mini computers started to get to the point where they were taking over mainframe approaches, we had personal computers, PCs, and PCs were so much smaller that all those old solutions suddenly looked very useful again. And as we've gotten used to that, we've gotten cell phones. As the cell phones have become larger, now we have smartwatches and we have devices for Internet of Things. If you look at popular programming languages, C hangs in there. And I don't know why, because it's a terrible language, but it tends to be a very low cost fit for the hardware. Okay, it tends to not make a lot of demands on hardware. And so as we bring in new hardware that we couldn't build before, like a lot of these Internet of Things things like smart light bulbs, the hardware becomes minimal again. When the hardware becomes minimal, using C starts to look good. And when we use C, a lot of you are probably going to be frustrated they haven't let you use a lot of nice, slick libraries. You don't get those slick libraries in C because they don't fit well into that kind of hardware environment. So keep it simple, prefer simple solutions to complex solutions, prefer pre-written solutions such as libraries and language features to writing your own. The ones that are already out there are already, or at least somewhat tested. It's easier to use something typically than to write it yourself. That means your time is more efficient. You get more done during a day. You should never need to write your own sort hash or database or a number of other things. Now that I've said this, you're probably feeling all frustrated because I've not let you do this. I've made you write your own stuff. So why not just use libraries for this course? And this is something I asked myself when I started this 14 years ago. I thought, 10 years from now, I'll probably give up on having them write their own libraries. They'll just be able to use existing libraries. We'll just look at how to use them. We won't worry about these details of being able to write them. I've kind of changed my attitude a bit for a couple of reasons. One, someone has to be able to write, maintain, and understand the libraries. And that someone is someone who majors in computer science, not someone that picks up programming on the side, not someone that does these related majors like information systems or information technology. Most schools will have a half a dozen computing related majors, and in a lot of cases the difference between them is whether you can do something a little more involved like we've done in this course, a little more involved maths and things like that. A lot of overlap between some of them. It's basically to get people that can't quite cut in computer science into the game. So someone has to be able to write, maintain, and understand the libraries, and that person majors in computer science. Also, someone has to go where, here's a quote, where no man has gone before. You might recognize it from Star Trek. But libraries make unnecessary assumptions. They have to. When you write a library, you make certain assumptions about a variety of things. And then as things evolve, that might not hold for the future. If I knew that all of you were only going to work on Pentiums that support lots of memory and have demand paging and all sorts of other lovely features and would never connect them to a network, a number of other things, then we could say, oh yeah, you'll never need to write any of this stuff yourself. You can just use libraries. But environments change. Things are distributed now, moving into cloud computing. That seems like you'd have more resources. In some ways you do, other ways you don't. There's the whole Internet of Things where we put software onto very small devices. There are a number of other things like that. A number of years ago, I had a interview with Google, a phone interview with Google, and they started off with a problem, and I immediately recognized, oh, this is a classic example of where you would use a hash table. And they said, well, how would you approach this? I said, well, that's a classic example of using a hash table. You got to look things up. You're not looking for a particular sequence or order. There's nothing like alphabetizing or anything like that. And the problem description, you just have to find it really quickly. And it seemed very big. And they said, well, that's fine, but what if you have a lot of these things you have to look up? And it's like, well, hash tables, size of the array, arrays are, a size of a signed integer, right? I'm thinking that should be plenty big enough. And they go, no, that's nowhere near big enough. And they crank it up. And I'm like, well, you find a language that used unsigned integers, 32-bit integers, and they're like, no, it's got to be bigger than that. I said, well, you can go longs, you can get this big, you can get, it gets bigger. And they were like, no, it has to be much bigger. At this point, I'm thinking, well, their problem is contrived. It's just to make me look foolish. But what they noted is this is a problem that Google has. Specifically, they need to look up search strings that other people have already put in. And if you think of all the Google users in the world, since Google started, and all the strings that they've typed in, all the search strings they've typed in, that's a lot of different search strings. And what if you want to know which ones are common? Show us, keep counting. So when someone puts in a search string, see if someone else has already put that search string in. If so, how many times? So basically, you've got a search string and a count. And if you're Google, that's a very big number. And a hash table library is not going to handle that. You're going to have to go to a distributed. A little while after I had the interview, I came across the idea of a distributed hash table, which we'll touch on briefly in network programming. But basically taking what's logically a single big hash table and breaking it up so that different servers deal with different parts of the hash table. And I haven't found libraries that do that, okay? So environments change, problems change. We go on to harder problems. If we would limit the problems we approach to the problems that we were able to solve in, say, the 1970s, but we had Pentiums to do it, yeah, we could probably just use libraries and we'd probably be fine. But every time that things, the technology develops more, People want to solve harder problems, and you need more things. Genetics, for example, a lot of programming involving genetics these days. I haven't gotten into it too much, but the data structures they use to keep track of a gene and all the proteins in a gene, for example, they're very interesting data structures, and there aren't standard libraries that work well for that. You might just get something that's not available. Proteins are an example, but also it's hard to find good graph libraries. There are some graph libraries out there, but they often have a lot of limitations to them because they're just making too many unnecessary assumptions, and they aren't a good fit for problems. And so people tend to end up rolling their own stuff for graph libraries. For instance, Google Maps. You say, oh, well, you could implement Google Maps on top of someone's graph library. Yeah, it turns out that that's not what Google ended up doing, because the graph libraries that are available, I'm sure they looked at them, the graph libraries available simply couldn't handle what they needed to handle. Yet clearly it's a solvable problem. Google Maps is out there, and most of us have used it. It tends to work. So someone has to go where no one has gone before and solve the unsolved problem. And you can really only use libraries to solve a solved problem, or it wouldn't be there as a library. Okay. So with that, I would just finish the course by saying, welcome to computer science. As I mentioned at the beginning, the first two courses, 130, 150, they're kind of literacy courses. They're kind of like learning to read and write, okay? Whereas you come to college and you take a literature course, we get into things that they didn't get into prior to that, things like plot and character development. There's a whole another level of looking at things. And that's really what we've started in this course, things like understanding Big O, things like understanding how you deal with elaborate collections. In a sense, this is the first college level programming course that we have here, right? COS 130 and 150 are really to make up for the fact that they didn't teach you programming in your first 12 years of school. COS 210, the math part, that's college level, but that's kind of off to the side. So this is it. So now you're getting a taste of what actual computer science, as opposed to mucking around with code, is. Hopefully you've enjoyed it, or at least learned from it. And with this, we finish kind of the foundation of computer science, and we start looking at particular areas that we can apply this stuff to. So hopefully that'll all work for you. So with that, we end the course.